at waves yesterday, and there's two types of waves that really didn't get into it. I think I said yesterday, but the last time we met. There's the transverse wave, which is what we demonstrated out in the hallway. In which the individual particles travel perpendicular to the wave. So in the hallway, when we had that really long coil and I put a pulse into it, the wave was traveling this way, but in reality, each coil in it was just traveling up and down. So if the particles, or whatever the medium is, so the particles will move perpendicular to the wave. To wave movement. So if you've ever done battle ropes, the rope attached to the wall, and you hold this, you're just creating a bunch of transverse waves because the parts in the rope are just moving up and down, but it looks like a wave's going out to the wall and back. The other type of wave is a longitudinal wave. And I've been demonstrating a longitudinal wave since the very beginning. Matter of fact, you've been dealing with longitudinal waves since birth, and according to some, before birth. And you're probably dealing with both. Longitudinal waves, this happens when the particles move parallel to the wave movement. So just a quick demonstration. I have a slinky here. Got a couple more on the top. I have a slinky here, and I'm hoping everyone can see it. Is that background better or the black? Does it? All right, so I'm gonna first calm it down. I'm gonna let go of some coils at the top, and the question is, what do you observe? Didn't let go of that many of them. Let's try with a few more. Hopefully you got something out of that. What did you observe?
Can you see it again?
Okay. Fair enough. Calm down. I think part of the problem is I'm right-handed, so let's do it this way. That was a better one. What did you see?
The waves travel down.
So you saw something go all the way down to the bottom? Okay, that was a longitudinal wave. But in fact, the coils really just moved up and down just a little bit. So the particles, the coils in this one, moved perpendicular to the wave movement. Sorry, moved parallel to the wave movement. So the particles were moving up and down, and the wave went all the way down, all the way back. An example of a longitudinal wave, thus the comment of since birth or before birth, sound is a longitudinal wave. Your vocal cord is flipping back and forth when you speak, and it pushes particles against other particles, which hit other particles, which hit other particles, and so on. So the particles are just moving back and forth, but the wave travels all the way to your ear, hits your eardrum, pushes it in, sucks it out, back and forth, and our brain picks it up as certain sounds. Transverse wave, we've got the, I'll put down battle ropes as an example. And the fan wave, fan dynamic wave. Presumably, you've seen them on TV, if not in real life, when somebody stands up and then it just slowly progresses. People are just moving up and down, but you see a wave go hopefully all the way around the stadium. And then the S waves, for those who've done geology, and the P waves. So for a longitudinal wave, all you need is for some particle or unit, like the coil, to hit another one, to cause another one to hit, cause another one to hit, cause another one to hit. So longitudinal waves can travel through air, liquid, solids, that's the other one. So these travel easily pretty much in any medium, plasma, so forth. So solid, liquid, gas. Because in all of them, pushing one particle will cause another one to move. And it's easy to demonstrate in a solid, where if I just push here on this end, the other end moves very quickly. Transverse waves. In transverse wave, you've got a particle coming up, pulling the next one with it. So there has to be an attraction between the particles, or somehow connection between the particles, so that when one moves up, it's going to pull the other one with it. And as it moves down, it's going to pull the next one with it. Transverse waves work nicely in solids. Liquids, very poorly, and in gas, pretty much non-existent. If transverse waves work well in gases, then I should be able to do this, and Sushil should be able to feel it in a moment. But the gas does not draw other gas with it particularly well. So this works quite nicely in solids. Which gives us some major clues here about the Earth. Earth. If there is an earthquake over here, earthquake, and I've got a seismograph over here. So I'm picturing the ones that I dealt with years ago as part of my wife's summer research. You have a barrel going around and a needle on it, and as the air shakes, the needle will shake, and you basically see lines on the barrel as the barrel turns. So what they noticed is that there's two different waves that hit here. There is first you get hit by the longitudinal wave, then you get hit by the transverse wave. Well, since longitudinal waves can travel through solids, liquid, gases, plasmas, the longitudinal wave is going through the Earth, whereas the transverse wave has to go along solids. So the transverse wave is traveling along the crust at the top. And so the first wave to hit here are the longitudinal waves, and the second wave to hit are the transverse waves. So since the first ones get here, because it's based on one thing smacking into another, hitting another, hitting another, they're called P waves because they're either called pressure waves, pressure caused by something smacking into something else, or they're called primary because they get there first. It is convenient. The P stands for either. S stands for shear wave or secondary wave. Secondary because it gets there second. And shear is a displacement against the normal axis. So I've got a slinky right here. If I applied a shear to it, I'm pushing that way against it, causing the particles to move perpendicular to the normal axis. Normal in both senses of the word. Secondary wave. All right, questions to hear? I'm assuming Cassandra speaks for all of you. So obviously, waves travel on things. Sound travels through air. Any of you ever put your ear on a train track to hear if trains are coming? Only do it when there's no train nearby. Or the classic, you watch old westerns, people putting their ears on the ground to know if there's a stampede or the bad guy's coming. I got one nod of recognition, 1.5 recognitions. Okay. Basically looking for sound. Oh, actually, in ancient China, they would put barrels in the ground And if anyone was digging, that the barrel would pick it up and then vibrate and send, and you'd be able to hear it coming out of the barrels. So what we're gonna do here is we're gonna send the wave down to the other end and back. This is gonna be considered a fixed end, and that's gonna be considered a fixed end, right here. And to do that, we need electricity. There's another one, yeah. Extension cords galore. All right. Hope that you can see that this is vibrating. If you can't quite see it's vibrating, I can put something near it. All right. So what it's doing is it's sending a wave down to the other end. It hits the fixed end and then bounces back. Similar to what we were doing out in the hallway, Briley had the fixed end when she held it tight. I sent a wave down and it reflected. The wave goes down, hits a fixed end, it's going to reflect on the other side, come back and interfere with the next wave. So I've got waves being sent this way, reflecting, coming back. And we can start to see some patterns forming here. If I apply just a little bit more force, we get a better pattern. And let's see how close I can get it. All right, not perfectly there, but hopefully you can see. How well can you see that? I don't know if that helps. We might have to go to a lighter background. Does that help at all? No, that's actually white on white now, so never mind.
That one's better.
Black or blue? Black, okay. Let's clear that. All right. So we have a point here that's not moving much. That's the node. We have another node right there. There's a node at that end and a node at this end. Where it's vibrating the most, antinode. Now, hopefully, let's see if I can make that just a little bit bigger. Not that way. Make it a little bit bigger if I have a little bit less mass. Let's see, that is a 50. And 20. Okay, I think that's probably as good as we're going to get. So we clearly have these points that aren't moving much. We have these antinodes here. So hopefully it looks like we've got this band here where we've got the nodes that you're seeing it sort of come out and come back. So when we represent a standing wave, this is a standing wave with two fixed ends. The first harmonic, the simplest mathematically, would look like, that's the representation of it. That we have the point where we have the antinode vibrating back and forth a great deal. And then we have the fixed points. The second harmonic, that's the word harmonic. Well, every time you add a harmonic, you're adding half of a wave. And they should be symmetrical. I'm not sure I drew it that way. That would be the second harmonic with two fixed ends. The third harmonic, which is what we have right here, gonna look something like that. And as I mentioned, you add a half wave every single time. So this is half of a wave here, half the wavelength, or half a wave. This is a full wavelength. How many waves is that?
1.5.
Say it again?
1.5.
3 halves waves. So if I want to figure out what is the wavelength here, well, a wave is with fixed ends, or with nodes, a wave is going to go from node to node. Sorry, node, skip one and go to the next one. So that would be one wave right there. Since this is the third harmonic, or close to it, this is when the retentive side of me kicks in. Not quite at the point where I want to be there. You go higher. No, I want to go that way, so I need to add just a little bit. Okay, looks like the node's here now. So what I'm gonna do is I'm gonna measure this full length right here. I know this is 1.5 waves. And there it is. And measure the length from. Am I at the knot there?
Yeah.
And this puts it at, looks like 122 centimeters. So the distance from here to here is 1.22 meters. Therefore, I know that 1.22 meters is equal to 1.5 wavelengths, or 3 halves wavelengths. So what's the wavelength?
1.5.
So I've got 1.5 wavelengths. What is the actual value of a single wavelength? Or how would you find it?
You just divide those sides by 1.5.
Yep. One point.
83.
If you divide 1.22 by 1.5, it's not going to be 1.83.
0.81. Oh. I don't know.
0.813. Units? Like you mean it.
Meters.
Yes. Now, if I want to sort of figure out what the frequency is, I have these formulas over here. So I know that speed is distance over time. The distance, if I think about the time as one period, the time it takes for the vibrating piece to go up, down, and back. It's the wavelength divided by the period, that's the distance traveled in that amount of time. And the period is 1 over the frequency. Rehash of last week. We get the speed is equal to frequency times wavelength, or wavelength times frequency. I guess I usually do V is equal to frequency times wavelength. The order does not matter. So that's going to be true for waves in general. However, we have another way of actually calculating it. And I'm not going to go into the derivation of it. That properly requires calculus, well beyond the scope. But thinking through this, the force term deals with, as one particle moves, how much force is it going to pull on the next particle? If you remember out in the hallway, when I tightened up the spring, the wave traveled faster. The more tension there is, the more that as one particle moves, it's going to jerk the particle next to it. The inertial term is how much mass am I moving? The more mass I have, well, the more it wants to keep doing whatever it's doing, so the harder it is to get it to change. Therefore, in the case of the string, So for one-dimensional waves, it's the square root of the tension divided by not the mass of the string, but the linear density of the string. This is the linear density. Now flash back to previous courses. What's the formula for density? Sure, somebody's had it. Jennifer, you look like you want to say it. You don't remember it or don't want to say it?
I don't remember it.
Okay. And then there's the avoidance of icon. Density is the mass of an object divided by the volume. This is mass over volume. Now, we're basically dealing with one dimensions here, with one-dimensional string. The length of it is considerably longer than either of the other two dimensions. That's why we're doing the one-dimensional approximation here. This is regular density. There's also something known as surface density, which is the symbol, there are a couple of them used. It's the lowercase sigma, is mass divided by area. There's a pattern here. And then linear density so we'll take a shot at it. We went from volume to area. Generally, when you have a string,